All right, I hope this is recording. Yeah, I think it is. All right, so I'm going to try a little different approach on homeworks. It seems like I'm going to be needing to talk more at the start here, try to lay down some foundational questions. I've got 18 that I'm going to do for you. You should pause the video, try them on your own. If you feel confident, you still might want to listen to explanations, as there may be a layering, a contextualization taking place, a little geometric discussion on origins. Maybe not, I don't know, I haven't done it yet. But I've kind of gone from not necessarily easiest to hardest problems, but a little bit of that approach. So we'll have at it here in a second, and we'll see how you do. Okay, so let me pin this on the board. Okay, I think you can see well enough. I think I'll put another light on. And you can anticipate every one of these questions coming your way on Friday. I do think we'll see how people are coming along. So writing equations of tangent lines is an essential building block of this discipline. So I'll give you an example of one, and then you anticipate coming your way on Friday. So let's say I give you a cubic, y equals x cubed minus 4x squared plus 5x. Let's make it, plus 3. Okay, keep the numbers small. You should try to sketch that. Pause the video and sketch that. And I'll just keep working. So if you pause the video, you've got as much time as you need. All right, so when you sketch polynomials, you always start from local behavior, and then you move to end behavior. And the reason, again, is if you plug in a 0 to the polynomial, and then plug in 0.001, you'll see these terms aren't as contributory to the change in y values. This would then take over. So answering my own question, here's positive 3, the y-intercept going up at a 5-to-1 ratio, going up pretty quickly there. A little bit of a bend. How much, I'm not sure, but it definitely, this could be of interest, a little more analysis, but it's basically got that trend. And so let's write the equational line that's tangent to this function at x equals -1. So somewhere over here, we can definitely see that we're moving up at a greater rate than positive 5. So we should get an answer that's a little bit bigger, 5 for a slope. All right, I'm going to get my eraser. Here it is. So just the mechanics of writing the equational line tangent. If you want to take notes, ELT, coming your way on Friday. So I need two things. I need to know the value. What did I give you? Oh, at -1. So I need y1 and -1. We can do that right now. So that's -1, that's -4, that's -5, and that's 3. All right, so we got ourselves -7, I believe. Okay, so again, right now we've learned a little bit more. -7 here, so we're starting to see the function look more like, well, I'm still not sure here. So I shouldn't draw that yet, but we're down here. All right, and yeah, we're where we thought we'd be on kind of a upward swing. All right, so we now know that -1 gets me -7. So therefore, my answer, I'll put my answer above the problem. The equational line tangent, the tangent line has to have x plus 1 minus 7 as part of its creation. Then we need to get the derivative. The derivative of x cubed is 3x squared minus 8x plus 5. Okay. Constants don't change, and linear functions are all the over 1 up 5 over 1 up 5, right? They're constant rates of change. All right, so now we need y prime at -1. So that's going to be 3 plus 8 plus 5, 16-to-1. So over here, you're going up. That tangent line has a 16-to-1 ratio of change. There's your answer. Problem number 1. All right, problem number 2. I'll give you some function that I'm hoping to get you to get a little bit of review of your previous classes. The prerequisite is the ability to do graphs of e to the x, ln of x, and so on and so forth. So let's do ln of x again. Let's do ln of x, and let's go from 2 to 5. All right, and JTC, just the calculation. 5 left-hand rectangles. All right, and really what comes out of this question, twofold, moving towards integration, area under a curve. This is how it was proven by a guy named Riemann. And the other part is to give you a little review of what the ln function looks like and how we use it, which is causing me more concern than the calculus part. All right, so ln function. Pause the video, you try it. Asymptotic behavior at 0, always increasing, passes through 1, 0 on the x-axis, and we can do ln of things like 1 over 100, 1/2, 1/3, right? We can do very small fractions. So let me continue this much further down. Okay, and so when we talk about 100th, the ln of 100th, we're going to get a very big negative number. And as we move away from x equals 0, my numbers are always increasing, but less quickly. All right, and those are the y values of ln of x. And we're going to go from 2 to 5, 2 to 5, and we want 3 left-hand rectangles is what I think I asked. So there's 1 left-hand rectangle, 2, 3. I got to bring this out a little bit more. Okay, so area 1, area 2, area 3, we'll move the 5 out a little. Those 3 areas. And I'm using first altitude, second, and third. So the question is, what's the width? Well, the width is the total distance from start to finish divided by the number of partitions. I just made the number 1. That's a pretty easy width. Not going to change it. I'm not going to start the video over again. I was hoping it would be fractional, but we can add 1 to 2 and get 3, 4, and 5. Wonderful. All right, so what is the left-hand rectangle? The width is 1. My first altitude is the ln of 2, which is roughly 0.7. E to the 0.7 is roughly 2. That's the inverse statement. And then I've got ln of 3 and ln of 4. And I hope a bunch of you have had some success with that. We certainly practiced it. The trapezoidal rule simply uses the ones in the middle twice and the ends once. And you got to take the average of a left and a right. So we divide this number by 2, and then we do the ln of 2, and then 2 ln of 3 plus 2 ln of 4, and there's your ln of 5. And that would be trapezoids, which kind of already looks like trapezoids, right? But that's a more accurate reading. There's actually something called Simpson's law, which takes 3 trapezoids, no, 3 midpoint rectangles and a couple of trapezoids, and very accurate. Boy, very accurate. All right, and the exact area? Well, you'd need a calculator for this one because you don't know what the integral of ln of x is. But you would simply add up an infinite number of rectangles, and I'm drawing rectangles right now. These strips are rectangular in nature. They have width and height, and I will blow one up for you. Right, and somewhere in here, I'll blow one up so you can see a strip. Okay, it's got height. The height is the ln of x. The width is dx. And so the exact answer off your calculator would be 2 to 5 ln of x dx. That would get you the exact answer. Okay. Okay, so that's 4 problems right there. Exact answer. That's 4 things. I don't think I put the exact up there, so got a few more problems coming. All right. All right. So then the next question is a series of limits, and every single one of the next 3 limits is something you should have done in your last class. I learned today that some of my students didn't answer quickly enough on those, so I have pre-calculus classes in the spring. That tells me I'm going to spend more time on that. Right? Limits are slippery critters. So what's the limit? As x goes to infinity of, let's say 2 over x minus 7. All right, you're pausing the video, giving yourself some time, but I hope you look at this and you immediately know it's 0. I mean, that's x to the 1. This is x to the 0. We don't write it, x to the 0 is 1. And this exponent's smaller than that one. So I hope you can see that as x gets bigger, you know, put 100, 107 in, 1007, you know, you make this bigger, bigger, bigger. This isn't changing, it's a constant. Oh, what's the fraction going to? It's going to 0. From the standpoint of graphing, we have a height of 2, that's constant. we have x minus 7. Well, when we get out here, this y value, which comes from x minus 7, is a heck of a lot bigger than this y value, which is 2. Okay, so when I divide that into that, it don't fit. So that's one of the ones that you should know immediately if you spot it. Anytime the exponent in the denominator is bigger than the numerator, your calculation going to 0. How about 3x squared minus 4x plus 7 divided by 8x squared plus 2x minus 3? Again, from last year's study, you should have seen this as going to 3/8. And you could put numbers in like a billion. If you put a billion in, I don't think anybody cares about losing $3 or $7 in your pocket. You're a billionaire. I don't think that's affecting you too much. You know, you got a little hole in your pocket, you lost a $5 bill. I don't know. Maybe you got to be a billionaire because you cared about the $5. I don't know. But even these terms, you know, when you do a billion squared, that's 18 zeros. 18 zeros. But from a graphical standpoint, this is going up at a certain rate, right? In fact, it's the rates that matter. You know, this is a 6x. No, I'm not going to do that. That's going to change things. So we've got a 3x squared and an 8x squared. One's going up a whole lot faster than the other. You know, this one's going up more than almost 3 times as fast as that. So your ratio of change here is 3 to 8. So this would be a 3, that would be an 8. And so 3 to 8. Yeah, try some numbers, you'll see that that's what it is. So when the exponents are the same, it's the division of the coefficients. Easy thing to remember. All right. And then the last one might be something like doing x squared minus x minus 6 over x minus 3. Okay, and what you did last year would have been to find points of discontinuity in your rational functions. Remember graphing things like this, where you got something like that, but then there's people call it a hole in the graph. All right, well, you're actually finding what happens as I move towards, well, we're doing infinity here. Okay, so I want to change that. I didn't think about that. So this is going to be as x goes to, I gotta remember, -2. Oh, I'm lucky, I got a picture. So we're trying to find this y value. It's not this isn't the picture of that, by the way, but it's the idea that there is, you know, undefined situation when I put, oh, yes, God, excuse me, as x goes to 3. All right, so forgive me for that. Late in the day, I start doing hundreds of problems during the day and sometimes misfire. So I'm looking at 3 because it's undefined right now. Right? If I put a 3 in, I get division by 0. Can't do that. So what do? Well, can we rewrite it? Yeah, of course you can rewrite it. It's x minus 3 times x plus 2 over x minus 3. All right, and what happens? Get a little cancellation. Yeah, I can put a 3 in there now. And I get a 5. And that was your answer. Okay, so you can do them algebraically. Okay, we're going to be looking at a more conceptual limit soon, but I think I want to try to get us a little place where you're a little more comfortable seeing the same problems over and over here. I would think another day on this, and we've been doing left-hand rectangles, right-hand rectangle. Some things should be falling into place right now, right? There should be a picture emerging in your head of a number of these problems that you can put in the pocket I can do. All right, so let's see, what's the next thing I was going to ask? Average rate of change. Okay, I'm hoping that's in your pocket. So let's do a fairly basic one. Let's do 3x squared minus 2x. And let's go from 1 to 4. Let's find the average rate of change. All right, so from a graphical standpoint, that's a 0. So I now know I'm going down at 2 to 1 through the origin, and then back up again. So there's the graph. It doesn't hurt to know what the graph looks like. All right, but to answer this question, no, you don't need to know what the graph looks like. But, well, I am going to draw a picture here in a minute, so helpful. So we put in a 1, and we get 1 out. All right, so 1, 1. Boy, this thing turned quickly, huh? 1 means that that thing must have done that very quickly. Whew, didn't anticipate that. Huh. Well, minus b over 2a minus b over 2a, 1/3. Yeah, so this thing bottomed out at x equals 1/3. Wow. Okay. Well, is what it is. Put a 4 in. You got 48 minus 8, 40. So it sure looks like we got ourselves 39 to 3. So we got ourselves an average rate of change of 13. Anticipating my next question, yes. When is the instantaneous rate the same? So here's our picture. Here's 1, 1. It's not an easy picture to draw for this problem. So we're really looking at something here to here, right? In that secant line. But what we're after is the tangent. Oh, we're after the tangent that is the same slope as that. So it's somewhere in here. Somewhere in here. That's the picture that goes with this. A better picture would have been something like this. Right? Mean value theorem for derivatives. We're going to find letter C, which is an x value, right? Because A and B are taken. So the textbooks call it C. All right. And I'm going to state the formal definition of the mean value theorem for derivatives. If the function, in this case, the function is 3x squared minus 2x, is continuous from 1 to 4. And it is. Continuous means those numbers are used. I should have probably put brackets there to begin with. Again, late in the afternoon, tired. So that's a closed interval. And if it's differentiable over the open interval, the open interval looks like this. Yes, I can, nice smooth curve, I can take derivatives. Then there has to be at least one place. There could be more. This thing could have done this, right? There's lots of places where I'm going up at the same rate. But there has to be at least one, coming back to the original picture, where I'm going up at 13 to 1. And how do you find instantaneous rates of change? How do you find one layer of geometric change? You take a derivative. And the derivative we're looking at is 6x minus 2, or the textbooks would have said 13 equals 6c minus 2. No biggie. All right, so you add 2, you got 15, you divide by 6. That's your letter C, which is equal to 5/2, which should be right in the middle of that because quadratics have that kind of symmetry. No other function does. But all right, so that's our value. 2.5. So at 2.5, if this is 1 and this is 4, halfway around, I'm going up at a, whatever I said, 13 to 1 ratio. All right, next problem. A series of polynomial terms. Now let's see if you can handle taking a derivative of each. And I probably am discriminating against, I probably should have you take integrals of each. So I'll do both. At the same time. So one layer of change is taking a derivative. So we'll start with y equals 5x to the 4th. Okay, and let's call it little f. And we're going to find that, and we're going to find that. Here to here, taking a derivative, 20x cubed. Here to here, taking an integration, 5x to the 4 plus 1 over 4 plus 1 plus c gets me, x to the 5th plus c. So that's like grandma's position, her velocity, and her acceleration. Okay. All right, now we'll up the level of difficulty slightly. And we'll call this one f. We'll call this f prime and f double prime. Just another way of thinking, position, velocity, acceleration. And I'll give you 3x to the minus 2. So one layer of change. One layer of change is like measuring, putting this over the box here. Let's see. Okay, so here's a box. I layer it with a little more volume, right? And then I measure this, and that's the rate at which this box is changing at this time. If I kept putting on top, adding up the layers, well, I'm taking the volume here and I'm making it into a bigger box. And I might ask questions like, How much volume did I add? That's integration. All right, so multiply, drop down 1, add 1. If I add 1 to that, I get that. If I divide by that number, I get that. Hopefully you're getting able to follow, either you're following it quicker or you're starting to do it on your own, but that's where you want to be. Let's keep adding a little difficulty here. Let's go to 1 over x. That's a tricky one, right? And we really need to write it that way. So this one then becomes easy, minus x to the minus 2. But what happens when I add 1 and divide by 0? It's undefined. So we cannot use the power rule here. We cannot use the power rule. We just have to know where that came from. We talked about it graphically today. That's the ln function plus c. These are called indefinite integrals. Indefinite. In other words, we're not exactly sure which curve we're looking at, but we're certainly getting one out of that family. All right, so what else? One more of these. And I could have written this as, what's another way? I could have written this as y dy dx and second derivative. That's the notation for the second derivative. And I'm going to give you 1 over the 4th root of x cubed. You pause the video and try it. I'll keep going right along. But you would have had to rewrite this one as x to the negative 3/4. That's what that means. Okay. The exponential activity is occurring in the denominator. I'm taking a 4th root and I'm cubing. All right, well, 1 layer is no trouble now. Minus 3/4 x to the, I'm going to subtract 4/4, right? Subtracting 1, so that's minus 7/4. Going up 1 takes me to x to the 1/4. If I add 4/4, right? If I add 4/4 to that, I get that. What do I do with that number? Divide by a 4th. Okay, if I divide by a 4th, I guess I'm multiplying by 4. And plus c. Now you can always check your integration by saying, let's take a derivative. What would I get if I took a derivative? Well, the c would cancel out. 1/4 times 4 is 1, which is what this is being multiplied by, 1. It's really right there right now. Okay, and then what am I doing to 1/4? Subtracting 4/4, which is minus 3/4, which is what we wanted. Okay, so there's another one. All right. And then you're going to get some calculations that are hard to, I don't know what this one looks like. I don't have any values in my head, but it doesn't mean I can't take the derivative. So you pause, think about what you're going to do, try it. I see a product, so I'm going to do the product rule. Derivative of sine is cosine. Times, leave the other one alone. And then do the other one. Times, leave the first one alone. That's it. So if we have a product, let's say product equals length times width, then P prime is really about L prime W plus W prime L. It's really what's going on. It's rectangular stuff happening. You won't see the rectangular work in the text, but it's what's going on. So that's the product rule. I mean, if you want to write these things down so you can YouTube video and get more practice. Do you need more practice with the mechanics of the power rule? Go to YouTube. The only thing is they're going to be working with the chain rule and we haven't gotten there yet. Chain rule is the last real major thing on derivations that we got to look at. Implicit as well, implicit differentiation, which I was going to show you tonight, but I think I'd rather have you do this, which is why I'm making this video. So let's look at y equals x squared over the cosine of x. Okay. I don't think we have a product anymore. I don't think that's a product. I mean, I could make it one. I could say x squared times 1 over cosine x, but I think we call this something else. Quotient rule. Quotient rule. Did I mention you're going to get a quotient rule every test till the end of the year? Oh. All right, so the jingle. Low, D high. Minus high, D low. Over low, low. Okay, later in the term, I hope at some point I can really dive into the numerics of that and match it up to the picture. Right? Maybe I'll just make a video of it, and if you're capable of following it, great. There's no reason you can't mechanically get this right. Low, which I now said is Lou. Hi, Lou. Tired man here. Low, cosine x. D high, derivative of the numerator, times 2x, minus high, the numerator, times the derivative of cosine, which is minus sine x, all over low, cosine squared x, and you can stop. You don't even have to say plus. Just show the rule. We are giving you credit for getting this far, that you know a minus times a minus is a positive, but you don't have to do that. If you want to, fine, but if you make a mistake, it's wrong. So it's up to you. That's a quotient rule. And then we want to be able to string together what's called an indefinite integral. So here's an indefinite integral right now, which means I'm not giving you limits as in signposts. So we got 5x squared plus 4x minus 7 in parentheses dx, which means you're really integrating 5x squared dx, and then you're adding the integration of 4x dx, and then you're adding the integration of minus 7 dx. Right? It's really doing them each separately, which we did earlier in the video. So you should have no trouble. You should be able to see that is 5x to the 3 over 3. I hope you see that quickly now. I hope you see this one quickly, 2x squared. And I hope you know that that came from a linear function. And I hope you know it's a family of curves, because if you take a derivative of a constant, this thing could be any number. It's going to disappear. And if you take the derivative, multiply the 3's, you get 5x squared. Multiply the 2's, you get 4x. And slope of a linear function is its derivative. All right, so that's that. Now we're going to do a definite integral. I might talk about this one a little bit more. So can you handle this? Can you handle from 2 to 4, 2x plus 6dx? Can you handle that? All right, try it. I'm going to keep talking. From a conceptual standpoint, we're looking at 2x plus 6, which is a linear function. We're looking from 2 to 4, which is a trapezoid. So I could use the trapezoidal rule here. I might as well see what it is. So we got this. If I put a 2 in, I'm at an altitude of 10. If I put a 4 in, I'm at 14. So that's 24 times the width, which is 2 cut in half. So should get an answer of 24 here. Okay, and what we're going to do is we're going to add up an infinite number of these. This is a rectangle right there. It's got a dx for width, as in 0.1 kind of concept. And the altitude is coming from whatever this x value is. To get that altitude, I'm plugging it into 2x plus 6. So really, this is a statement about rectangular area. Now, that rectangular area could represent volume. It could represent anything, right? Depending upon what the rate is all about. But from a geometric standpoint, I'm just adding those up as I go from 2 to 4. So that came from x squared. That came from 6x. That's my table. I want to know my table values at 2 and 4. When I put a 4 in, I get 16 plus 24. When I put a 2 in, I wish I had a minus sign so people would have made some sign errors here. So you spot those early in your studies. I get a 4 and a 12. Okay, so that's 30 minus 16, which is a different answer than I got over here, isn't it? I do something stupid. Width is 2, divided by 2 is 1. Altitude was a 4 in here, 14, a 2 in here, 10, 24 times 1 should be 24. That's 14, isn't it? No, 40. There's my stupid error. Old guy getting tired. There, okay, now it jives. Okay, so same area, 24, which is what we said it would be. But we did it with some calculus. All right, now. All right, practice your graphing skills again with y equals minus x cubed and plus 64x. All right, let's see how you do. Well, what you should have done is minus x, remember, you're pausing the video. 0x squared plus 64x plus 0. And then you read it from right to left. So what do we have? Y-intercept at 0. Doing what? Going up at 64. Very steep climb. Minus x cubed, however, does this. Okay. And we can see that we have a local min on this side. So we know what we're after. We got to find that x value. We got to plug it in to find the min right there. That's your challenge. All right, so go ahead and see if you can do it and see if you can prove that it's a minimum. I'm not going to wait. You're pausing, right? All right, so the first thing I got to do is recognize that slope here is 0. So I'm going to take a layer of change and find out what x value gets me a slope of 0. So I'm going to do y prime minus 3x squared plus 64. I'm going to set that to 0. And it's an ugly number. Oh, what a shame. Did I get an ugly? I thought I had cubics. We did. Oh, no, we did 12. We didn't do 8. Then we did 27. That worked out nicely. All right, I got to change this up slightly. I want something that 3 goes into nicely. So I'll make this 57. Let's see if that helps. I'm going to make that 50. Doesn't change the problem too much. 5 and 7 add up to 12, and 3 goes into 12. So I know that's divisible by 3. I'm hoping we get some integer-friendly answers here. If not, we'll bail on this problem, but I'll just explain conceptually. All right, so we subtract 57, we divide by 3, and I think that's 19. Yeah, so that's 19. And we're going to take plus minus, so it's not friendly. Square roots of 19. What a shame. All right, so down here, we now know that that one is negative 19. Right, negative square root of 9. No, negative 19. Right, square root, sorry. Minus the square root of 19. Well, where would you go from there? Well, you wouldn't know this was here until you prove concave up. All right, you got to prove that this is concave up here. There's 2 ways to do it. One is, I'm at 57 minus 3x squared. When the first derivative, this is called the first derivative test. When the first derivative is increasing, then the original function is on a concave up interval. So that's one way. The other way is to get the second derivative, which is easier. All right, and that's minus 6x. When does that equal 0? At 0, so that's where concavity changes because I went from negative to positive, right? On minus 6x, excuse me. I'm looking at the graph of minus 6x. That equals 0, and I'm going from positive to negative in this case. If my second derivative is positive, I'm on a concave up interval. Okay, now how can I find out if it's positive? I can plug negative 19, square root of negative 19. Well, yeah, at that x value, this calculation is positive. So I'm on a concave up interval and I have a slope of 0. That proves I'm at a local minimum. What is that local minimum? You're not going to use square root of 19 in this function. Okay, so it wasn't integer friendly. I wouldn't give that to you on a test unless it was calculator portion. Okay, and we're not going to use the calcs too much in the regular calc class. The AB is going to have to deal with some calculator. We're going to do a little more there. Okay, but same concept. And hope you followed that. All right, so we're also going to do equations aligned to trig functions. Right now, we're sticking with sine and cosine. We will be working with tangent a little bit later, but let's just pose a question here. Let's say that we start with y equals cosine x, and I want you to, we'll stick with 1 period because we want to draw this. So let's say at x equals, oh, how about, what can I do? 4 pi over 3. Write the equation align tangent to the original function at x equals 4 pi over 3. And I will try to bring in a little trig review in this with you. The prerequisite, obviously, is you know how to do that already. It hasn't been my experience that students coming in can, so we'll have to learn to do that at the same time. All right. Again, trying to understand 4 pi over 3. Try to understand what 4 times 3.14 divided by 3 is all about. And that's a little bit bigger than 4, that number. This number is a little bit bigger than 4. So what does that number tell you to do? tells you to take a trip around the circle using the radius as a measurement. So there's the radius. I'm going to go around 1 radius length, 2 radius length, 3, obviously 3.4 is halfway, but I'm at 3, so a little bit bigger than 4. I'm down here somewhere. I'm down there somewhere on one curve of the cosine, one period. And that's one period of the cosine. And I appear to be in the third quadrant. I appear to be first, second, third quadrants here, right? There's your quadrants. First 90 degrees, second, third. And it looks like I am, well, I know what the cosine of 4 pi over 3 is, halfway. Okay, so I'm there. And now I'm trying to write the equation of this line that's tangent. Shares that point, goes up at that rate. All right, so what do? Take the derivative of cosine, which is minus sine. Okay, we need minus sine and we need cosine. Pi is the top half of the circle. You're going to break it up into 3 parts. There we go, which means there's 6 altogether. And I'm going 4. 1, 2, 3, 4. There's your triangle. There's your right angle. Minus 1/2 is the cosine value. Negative root 3 over 2 is the sine value because it's a 60-degree reference angle. 180 divided by 3, right? 180 degrees pi divided by 3, 60 degrees. Okay, we're ready. So the tangent line, I'll do TL. I need the position. Well, first off, I'm going to build it off of that angle. There's the cosine value at that angle. No, it was 1/2, excuse me. Oh, my brain is tired right now. And we're going up at minus sine rate. Well, here's sine, negative root 3 over 2. So I'm going up at root 3 over 2, and I've asked you to memorize root 3 over 2. If you don't know what it is, you might very well need to look it up on a calculator right now, because I'll be testing you on it. Does it look like it's going up at the rate you are finding? Well, it's certainly positive, right? I know the square root of 3 over 2 is smaller than the square root of 4 over 2, by the way, just for the record. All right. 0.877 in case you didn't do it. That's the approximation of the slope. All right, 3 more problems. All right, so not all 3 classes today tackled this, not all tackling the same stuff at the moment. We are getting divergence. And do I remember, did we do it in this class? Well, now you're asking yourself, what class am I in? Anyway, y equals, I'm giving you a cubic again, 2x cubed minus 6x squared minus 4x plus 3. And I'm asking you to sketch it first. We'll sketch it. And then we will write the equational line tangent to the point of inflection. And we'll look at all the things we have to consider to make sure that we're correct. So I'm going to start at 3. I'm going to go down at 4 to 1. And then I'm even going to go down faster. So I've really got a boom. I've got a real drop here. But eventually what? That takes over. And this comes down. Okay, but I don't know. It's got to be higher than that because this was a 4 to 1 ratio. So I don't know. I don't know how high that goes up. All right, but I've got something that looks like this. All right, I kind of butchered it. So let's get this out of the way. We'll put some numbers in here. Okay, and we know we had a 0, 3. And we're going down at 4 to 1 right there. That's about all we know right now in the general shape. I'll put the original up again. 2x cubed minus 6x squared minus 4x plus 10. Now this comes from completing the cube. Putting cubics in graphing form comes from completing the cube. I'll just leave it at that. But that completing the cube process highlights minus b over 3a. If you want to look at it, you can look at, I got one on the YouTube channel. Minus b over 3a is 6 over 6. So x equals 1 is what we're going to find using calculus. I'm not using calculus there. So we're going to come up with x equals 1 as the x value of the point of inflection. So what do we need to know for equation of a tangent line? We need to know location, and we need to know the slope. And slopes are going to come from our first derivative. The location is going to come from the original function, is going to tell us location. And y double prime is going to help us sort out these values by looking at acceleration. Okay, a point of inflection is where you change from concave up to concave down. That's happening somewhere in here, concave down to concave up. We have to find that x value. We know it's 1. How are we going to do it with calculus? First derivative, 6x squared minus 12x minus 4. Second derivative, 12x minus 12, set it to 0. There's your x equals 1. That's a candidate for a point of inflection. Unless we see that the signs change at 1. And you can do a sign chart if that's easier for you. 1, when you put a number bigger than 1 in, you get a positive. When you put a number less than 1, you get a negative. So not only does it equal 0 when I put a 1 in here, but bigger than 1, it's positive, which means I'm on a concave up interval, negative concave down. If your concavity changes, you're at a point of inflection. Whoa. I won't do that again. All right, so 1 is our nice number. We now know this. How do I find out where it belongs? I plug it in, and that means I'm just looking at the coefficients. I've got 12 minus 10 is 2. So I didn't like that. 12 minus 10 is positive 2. Something inconsistent here. Oh, I'm sorry. I was looking at location. I thought I was looking at slope for a second. Just a tired brain. I knew I wasn't increasing it 2 to 1, so that bothered me. Okay, but all I did was do y of 1 here, and I forgot where I was. So y of 1 got me a 2, I believe I said. So that is the coordinate at which we are going down. And if I want to know at what rate I'm going down, I have to look at the slope function and do y prime of 1. And that's equal to 6 minus 12 minus 4. That's better. That's minus 10. Okay, so the equation of the tangent line, I have a slope and a point. So the tangent line is equal to minus 10 x minus 1 plus 2. Okay, and I put cubits in graphing form long time ago, back in the 90s. And about 2 years ago, I realized that the graphical form can come from this just as easily. So if you were to take that, which is a stem, and simply use 1 in the cubic, if you multiplied this out, I'm sorry, I got to put the 2 there. If you multiplied this out, you should get this. Yeah. Oh, well, just mentioning it. All right, let's see. Not going to get into the graphical form of a cubic. That's pre-cal. So next question. Minus x squared plus 8x minus 7. So y equals minus x squared plus 8x minus 7. I would like the absolute max for this function, and I would like you to prove that it is an absolute max, or at least prove that it's a max. All right. Again, when you have maximums and minimums, here's maximums and minimums, where they are, right? Well, what can we say? The slope there is what? 0. The slope there is what? 0. Slope here is what? 0. It looks like if we want to find a max or a min, the slope there is 0. So we better look at the slopes. Minus 2x plus 8. When does that equal 0? When x equals 4. So we now know that this thing, right? We also knew from minus b over 2a should also get 4, right? Minus 8 over minus 2. Okay, so there's lots of ways to skin the cat, and not that I would ever want to skin a cat. So I'm sorry that somebody came up with that cliche. How do I prove it's a max? Again, concave down with a slope of 0 proves a max. Concave up, slope of 0 proves a min. So we'll do that. Or we can look at the first derivative and it's always decreasing. If the first derivative is always decreasing, it's always concave down. That's a quick way too. All right, but let's actually look at the second derivative. Second derivative is -2. So I guess it doesn't matter what x I put in. Doesn't matter. Whatever x I put in, 0, 1, 2, even a 4. Even a 4, -2. Always concave down, slope of 0. That tells me that my max is what I get for a y value when I drop a 4 in. -16, 32, -7. There's our nice 2 to 1 opposite. We know that's correct. So 16 minus 7, 9. Okay, so this thing is a quadratic. Passes through 4, 9. It also goes through 0, -7, and that's on the upside with a rate of change of 8 to 1. So this is going up at 8 to 1, and it's 0, -7. All right, so that's kind of neat. So the graphing form for this was x minus 4 squared plus 9 with a minus sign, which means, that's enough. Yeah, so if I went over 4 units, I should have gone up 16 when I squared. I didn't go up 16, I went down 16. So I didn't go up 16, I went down 16. That's where that -1 is coming from. Not that you need to know that. Oh my God, we got a nice storm out there. Got my windows open in my car, pouring cats and dogs. Oh, how nice. Sitting on a towel on the way home. All right, we got one more problem to do. Then I'll upload the video. Hopefully it recorded properly. We'll find out. I don't know where that storm came from. All right, this is kind of new for you, but you actually have everything you need to be able to solve this equation somewhere locked in that brain. So I'm going to give you dy dx equals 4x minus 2. So we have an equation. We have an equation. Dy dx is the derivative of y. And I'm going to tell you that y of 3 gets you 10. I'm going to ask if you could actually write what y is. So you're going to pause the video. And I'm going to watch my car get soaking wet. Almost hail out there. I see a funnel cloud, I'm ducking under the table. All right, so I'm just going to do the problem. This is called the differential equation. And you solve differential equations by how do we get from derivatives back to position? How do we get from velocity to position? Integrate. I can't integrate it the way it's written right now because my variables are not together. Right? You always put your variables together in an equation. So I'm going to do dy equals 4x minus 2. I'm going to put it in parentheses with a dx. Now, both sides of this equation are begging you to integrate. When you integrate this side, you actually get y plus c, 1. When you integrate this, you actually get 2x squared minus 2x plus c2. We're going to put c1 and c2 together and just call it c3. Woo! I like it out there. Let me show you what we got here. This is fun. Oh, it's slowing down now. Yeah, slowing down. But we had a nice little burst on the windows. Yeah, good enough. Ooh, look at the trees. They're starting to swing a little bit. I like it. Last problem. Here we go. Yeah, so we're going to integrate. And if we integrate, we can go right to the chase. Y equals 2x squared minus 2x plus c. Okay, but I know some information. I know if I plug a 3 in, I get a 10 out. So I get a 10 out when I plug a 3 in. I think that's going to allow me to solve for c. And you can see that. Good. So we got what? 18 minus 6, 12. Subtract 12. Looks like c is minus 2. So what was the solution to this? It was 2x squared minus 2x minus 2 if I didn't make any careless math errors. And at this stage of the day, that's a 50-50 proposition. All right, so I hope that homework is going to help. All right, because I think I got to slow it down for you that where I do more of the problems and talk about them. But soon, maybe not tomorrow, but that day after, I'll make a 18-question worksheet. We're going to add problems to it, and you're going to do those on your own. And there's got to be some people now in the class that can do those problems. Okay, so all right, there we go. End the video.